Neuralink, the neurotechnology company founded by Elon Musk, aims to develop brain-machine interfaces, or BMIs, to enable direct communication between the human brain and computers. A crucial component of this technology is the electrode arrays implanted into the brain, which must meet stringent biocompatibility standards to ensure they are safe and effective over the long term. Biocompatibility refers to the ability of a material to perform with an appropriate host response in a specific application. In the context of Neuralink's electrodes, this involves not only the immediate biosafety of the implant, but also its long-term usability, including its interaction with brain tissue, potential for causing inflammation, corrosion resistance, and mechanical stability. Biocompatibility concerns. The primary concerns regarding the biocompatibility of Neuralink's electrodes revolve around their potential to cause adverse biological responses once implanted. The brain is an extremely sensitive organ, and any foreign object, such as an electrode, can trigger an immune response. This immune response can lead to inflammation, scarring, and ultimately, the failure of the implant due to the body's attempt to isolate or remove the foreign material. This is a critical issue because the electrodes need to maintain functionality over years, if not decades, to be viable for medical or enhancement purposes. Material composition and biosafety. Neuralink's electrodes are designed using materials like gold and platinum, which have a history of use in medical implants due to their excellent biocompatibility and resistance to corrosion. These materials are chosen specifically for their ability to remain stable and non-reactive within the body's environment. However, even with these materials, there is a need for rigorous biocompatibility testing to assess their performance over time. According to ISO 10993-1 standards, materials must be evaluated for their chemical, mechanical, and biological characteristics to ensure they do not pose a risk to the patient over the long term. One of the most significant challenges for the long-term usability of Neuralink's electrodes is the mechanical stability of the implant. The electrodes are designed to be flexible to minimize damage to the brain tissue, but this flexibility also introduces challenges in maintaining their position and functionality over time. The brain is a dynamic environment constantly moving and changing, which can cause wear and tear on the electrodes. Studies on similar biomedical devices have shown that even minor mechanical failures can lead to significant biological consequences, including the risk of infection or device malfunction. Moreover, the interface between the electrode and the brain tissue is another critical factor in long-term usability. Over time, the body's immune response can lead to the formation of a fibrous capsule around the implant, effectively insulating it from the surrounding neural tissue. This can result in increased impedance, reducing the effectiveness of the device in recording or stimulating neural activity. To mitigate these issues, Neuralink is likely exploring coatings and surface modifications that can minimize the body's immune response while maintaining the electrical conductivity needed for the device to function effectively. To address these biocompatibility challenges, ongoing research is essential. Advances in materials science, such as the development of more biocompatible polymers and coatings, are likely to play a significant role in improving the long-term usability of Neuralink's electrodes. Additionally, innovations in electrode design, such as incorporating biodegradable materials that can be gradually replaced or absorbed by the body, could further enhance the safety and effectiveness of these implants. Another promising area of research involves the use of mesoporous silica nanoparticles, which have shown potential in other biomedical applications due to their excellent biocompatibility and ability to carry therapeutic agents. Incorporating such materials into Neuralink's electrodes could potentially reduce inflammation and improve the long-term integration of the implant with neural tissue. The biocompatibility and long-term usability of Neuralink's electrodes are critical factors that will determine the success of the company's brain-machine interfaces. While the materials currently used in these implants have a strong track record of biosafety, significant challenges remain, particularly in maintaining the functionality of the electrodes over time. Through continued research and innovation, particularly in the areas of material science and electrode design, Neuralink may overcome these challenges, paving the way for widespread adoption of this groundbreaking technology.